Welcome to lecture 9. In this lecture, we will start our discussion on synchronous machine and to be more specific, synchronous generators. Now, according to my understanding, synchronous generator is the easiest thing to understand. It goes exactly as the concept of Lenz's law or Faraday's law of electromagnetic induction. That is, there is a coil. With that coil, the flux linkage changes and a EMF is induced. Now let's look into this diagram. So the outer member here, this one is the stator, and on the stator there are many conductors on this. Out of this I have drawn only two here. So the voltage is supposed to be induced in these two coils, and the inner member is the rotor. The rotor is also having a coil, and this through this coil the current is passed, a DC current is passed, so that it produces a flux. This rotor can very well be a permanent magnet, but for our discussion we will always assume it to be a electromagnet excited with a DC current. So let's say that the current is entering the coil through this point and is coming out of the coil through this point. That is, the current is going like this and coming out like this. So how to find the direction of flux produced by this current? We have to curl our finger in the direction of current. If you curl your finger in the direction of the current, that it is coming out like this and going in, then you will find that the flux is in this direction. This rotor is rotating. We are looking at a particular instant when the rotor is at this position. It doesn't mean that it will always remain here, but we are looking at a time instant when the rotor is here. So the direction of flux here is like this. We know that since the rotor will rotate, the flux linkage with these conductors will change. And we have seen in our previous lecture, that the change of flux linkage with these conductors are sinusoidal function. We have seen that the area through which the flux changes varies sinusoidally. So the change of flux linkage with these conductors are sinusoidal. So the voltage induced are also sinusoidal. Let's look at our previous class once again. We have seen here that the orientation of the surface area changes. When the orientation of the surface area changes, then EMF is induced. We said that sometime the coil is like this, sometime it get turned like this, sometime it is like this. So the flux lines that are coming like this, they see different area. Here they see zero area, here they see some area which is a sine function, here the sine function is have a maximum value, and so on. So we have seen that the flux varies, the flux linkage, this is the flux linkage, varies sinusoidally, and for this variation of this flux linkage, the induced EMF also varies sinusoidally. And we have seen that if I assume that my flux varies as a cos theta, then the induced EMF varies as a sin theta. That is, if this is my variation in flux, this will be my variation in induced voltage. So if you look at this diagram, you will understand that the induced EMF will lag the flux by 90 degree. This is a cos theta, this is a sin theta. So this one, the induced EMF, is lagging the flux phi by 90 degree. Let's come back to this one. Here, this is the direction of induced EMF. What will be the direction of voltage now? Now we have to say in which direction it is moving. Let's say that the rotor is rotating in this direction. If the rotor is rotating in this direction, then my induced EMF will lag this voltage by 90 degree, will lag this flux by 90 degree. So how will we draw that? If this is my flux, my induced EMF will be somewhere here. And it will lag the flux by 90 degree. That is, if the flux is maximum here, induced EMF will be maximum here. Now whether it will be a dot or a cross, how will we understand? Now we have to look at this diagram once again. Here the induced EMF is lagging, so it is moving in this direction. If it is moving in this direction, then for this, if you are moving along this direction, then this member comes later than this member. That is, if someone is running like this, then a person here, say A is here, B is here, and he is running in a track like this. So who is lagging and who is leading? A is leading, B is lagging. So if the flux is here, my induced EMF will be along this direction. My induced EMF will be along this direction. You can always say that I can draw it like this. This is also 90 degree, but this will be wrong, because if you draw it here, the induced EMF will lead the voltage, will lead the flux by 90 degree, but the induced EMF has to lag by 90 degree. So my induced EMF will be along this direction. This is the direction of flux. This is the direction of induced EMF. Now let's say that I have placed one coil here. Let's say that I have placed one coil here, and the voltage induced here is like this red line. What happens if I place a coil which is 120 degree apart from this? Say this is 90 degree, this is 135 degree, so 120 degree will be somewhere here. So one pair of coil I have placed here. Let's draw it with red. So this is one coil I have placed here. Okay. Now what happens if I place another coil which is 120 degree displaced in space? 120 degree displaced means what? That if you move in the direction of rotation, this coil will lag this coil by 120 degrees. So this coil is lagging this coil by 90 degrees. Let's call it as A dash. This will be B dash. So the voltage induced will again be sinusoid, but the voltage will lag this voltage by 120 degree. So if this is the voltage induced in this coil A dash, the voltage induced in the coil B dash will be like this. Same sinusoidal voltage lagging this one by 90 degree. Sorry, 120 degree. Let's take another coil which is lagging this one by 90 degree, again by 120 degree. So let's say that this is C and this is C dash. Now the coil C dash is lagging coil B dash by 90 degree in the direction of rotation. The direction of rotation is like this. So if this is my B coil, C coil is lagging this one by another 120 degree. So the voltage induced in this coil, this is my C coil, this is my B coil, and this is my E coil. So the voltage induced in C coil is lagging the voltage in B coil by 120 degree. So I have placed three different coils. I am getting three different voltage phase shifted by 120 degree. If you place two coils that are 90 degree apart, then you will get two phase voltage 90 degree apart. If you place five phase windings displaced by 72 degree, then you will get five phase voltage each displaced from each other by 72 degree. If you place four coil, say each displaced by 30 degree, then you will get 4-phase voltage displaced from one another by 30 degree. So it is only the spatial displacement of the coil that creates this phase shift. Otherwise, there is no difference between the voltage induced in this coil, the voltage induced in this coil, and the voltage induced in this coil. So we have understood that the voltage induced is a sinusoid, and this voltage lags the flux by 90 degree. Now, what is flux? Flux is mmf by reluctance. What is mmf? mmf is nothing but number of turns into current. This is equivalent to our emf in electrical circuit, and reluctance is equivalent to resistance in our electrical circuit. So flux is equivalent to current in an electrical circuit. In a magnetic circuit, flux is equivalent to a current in an electric circuit. So this is the direction of flux, and if you look at this, the relation between the flux and the mmf is nothing but flux divide mmf divided by reluctance gives me flux. So we can say that the direction of flux, the direction of mmf, these are same. So sometime we will call them as flux, sometime we will call them as mmf. Both of them are, they are not same, but they are scalar multiplier of one another. Now let's look into our next thing, that is, now what we have said that this is our direction of flux. Sometime we will say it flux. I have written here it mmf, magnetomotive force. You can always show it as flux, and this is the direction of induced emf. This flux is called the field flux. What is the name of this? This is known as field flux. Flux produced by the rotor. Here the rotor is the field, so we call it as the field flux. Flux produced by the field in this coil, in this machine. And this is the induced emf in the stator. The flux produced by these two coils, since this is in rotor, we call it as the rotor flux, and this is the voltage induced in the stator coil, so this is the stator voltage. This is the flux produced by the rotor, these two coils, this is the voltage induced in the stator. Now let's try to draw a equivalent circuit from this discussion. Now for the rotor circuit, what we have, how will you produce this rotor magnetic field? What you will do, you will make a coil, and in that coil you will give a DC current to that. So this is the equivalent circuit for the rotor side. The rotor side, this is the equivalent circuit for the rotor side. What we have here, we have a voltage source, and then a inductance and a resistance. Since it's a DC circuit, the inductance will not have any effect other than transient, so it can always be shown as a resistance. However, the flux produced can be written as L into I, so we prefer to show it as a inductance rather than a resistance. Now, what about the stator circuit? In the stator circuit, three-phase voltages are induced. Since we are talking about three-phase synchronous machine, so three-phase voltages are induced. But when in our discussion, we will always limit our discussion to a single-phase machine, and then we will say that in three-phase machine, it is just 3 times of that. So if we take any one of this phase, say if we only take A dash, then it will be nothing but a AC voltage, and then since I have made a coil, it will have a resistance and a reactance. So if you look here, in the stator I have a coil in which voltage is induced. The voltage induced is AC. So that's why I have drawn here as a AC source, and since I have made a coil, that's why I have written a L and a R. Now what I am doing, I am making a generator. So what it will do, it will get connected to a load. It can be a resistance, it can be inductance, it can be another source. Let's write it as a load, not a resistance. So here there will be some voltage that is there across the load. We call it as the terminal voltage, VT. Now this is the induced EMF, we call it as EF. And here we have a current flowing, let's call this as the armature current IA. This is the resistance of the armature and this is the inductance of the armature. Now we can write it L, or it is better if we write it as XL impedance, that is 2 pi F into L. Now if you look at this circuit and this circuit, in this circuit we are maintaining a constant DC supply to keep the field constant. We will prefer to keep this field constant. So here a constant current flow through this circuit, so this part is not having any dynamics or is not having any change. Whatever changes occur due to change in load occur in this part of the circuit. Now when we are talking about this, let's try to draw a phasor diagram for this circuit. We will not draw anything for this. We will simply assume that the flux in the machine is constant and we will forget about this part. We will not consider this part under the assumption that the flux in the machine is constant. So we will not bother, we will not discuss anything more about this. We will concentrate our study to this part of the circuit. So what we have drawn, we have said that a synchronous machine is a three-phase machine. It produces three-phase voltage. Then we say that we will only look into one of the phases. Then we have drawn an equivalent circuit of that, which is like this: a voltage source with a impedance, a resistance connected to a load, let's call this terminal voltage to be VT, let's call this to be EF. Is it not similar to the problems that we have solved in first 3-4 classes? Let's first try to draw a phasor diagram of this. So how will we draw the phasor diagram? Let's take V as our reference. V. Now before we proceed further, we have to give a direction of power. Since it's a generator, let's assume that the power is flowing from this source to this load. So what will be the equation? The equation will be E of F will be equal to V of T plus IA into RA plus IA into X. This is X, this is R. So how we can draw the phasor diagram? Let's say that the current is lagging the voltage by some angle phi. So first of all, we have to draw the resistive drop. This is IA into RA parallel to the current. Then we have to draw IA into X. Now IA into X will be perpendicular to IA and will lead IA. So if this is IA into XL will be something like this. So this is my IA into XL. So let's look at this. This is VT. This line is VT. this is IARA, this is IARA, this is IAXL, IAXL, this gives me E. Okay. Now this is the angle between E and V, and this is nothing but the torque angle that we have discussed in our class, the angle between the two magnetic field responsible for production of the torque. We will see this how this is torque angle, but at this time let's call this as delta. So this is the phasor diagram of a synchronous synchronous generator at lagging power factor. Can you draw the phasor diagram of a synchronous generator? This is your assignment. Draw the phasor diagram. Draw phasor diagram of synchronous generator at number 1 unity power factor at 0 lagging power factor at 0 leading power factor and at leading power factor at any value. 0 lagging means if this is my current, if this is my voltage, my current is like this. That is, if this is my VT, IA is like this. 0 leading means if this is my VT, IA is like this. Unity power factor means if this is my VT, IA is like this. And for this question, leading power factor means if this is my VT, IA is like this at any arbitrary angle. So you draw this 4 phasor diagram and submit it as an assignment. Thank you.